Hi, so today I want to take you through a derivation commonly seen as a problem in first year physics classes. It's called the Atwood's machine. This is a situation where we have two masses hung over a pulley attached by a string. We're going to do the case where the pulley is frictionless and massless itself, so the only masses we have to worry about are these two different sized masses hanging by a string. The way I'll set it up is I have a mass big M on the one side and a smaller mass little m on the other side. You may be given the numbers, but I'm just going to use these letters. And the mass big M starts a height big H off of a table, and the mass little m starts a height little h off of a table. And we want to answer these questions. What is the acceleration of these two masses? We will release this system from rest, and then it will accelerate uniformly. The mass big M falling, of course. How fast do they go? So we want to know how long it takes for the mass big M to finally hit the table, and how fast it's moving when it does hit the table. So for this derivation, we're going to be considering Newton's second law and solving this by the use of forces. So the first step when you're going to use Newton's second law is, of course, to draw free body diagrams. So we'll draw the free body diagrams here, just a box for each mass, and we'll start drawing forces on it. The first force you'll notice that there will be here is gravity. Each of them have a weight. So the weight, of course, is equal to mg for either one, little m or big M, and it points down towards the Earth. The next force that we'll know both of these have is a tension. The string connects these two masses, provides a tension which is an upward force on either mass. We'll label that one T. So now if we do Newton's second law for each mass, we write F net equals ma. So F net on the mass small m is small m times the acceleration of that mass, am. And the next thing we'll note is that we need to pick a direction for positive. So I've drawn here a purple arrow indicating that I'm going to take clockwise as the positive direction. Usually in a problem, you would call up positive or down positive or something like that. Here, since we have something rotating and mass is moving up and down, we'll pick a direction of rotation to call positive. In this case, I know that the mass big M is going to fall, so I want down to be positive for that mass, so we'll do clockwise around the pulley as the positive direction. So, whenever we add up the forces on mass small m, the positive one is going to be the tension, and the negative one is going to be the weight. Similarly, for the mass big M, F net equals ma, and on this one, the positive direction force is the weight, mg, and tension is pointing in the opposite of the positive direction. The next thing to note is, of course, that these are attached with a string, and so in either case the acceleration is just a. They're going to accelerate at the same rate. So for the mass small m, we have little m a equals t minus mg, and for the other mass, we have big M a equals big mg minus t. You'll notice here that we have two unknowns in these equations, the acceleration and the tension, so we can't solve it yet. We'll need to eliminate one of these variables to solve, and then we can plug back in for the other if we so desire. So, now that we have our Newton's laws written down for each mass, small ma equals t minus little mg, and big ma equals big mg minus t, we need to solve this system of two equations and two unknowns. The first thing I will solve for here is the acceleration, so the goal is to eliminate tension from these equations. So we'll simply take the first equation for the smaller mass and arrange it to solve for t. So we will have t equals ma plus mg, and then we'll plug that into the second equation. So we have big MA equals big mg minus quantity little ma plus little mg. Now we're down to one equation here with only one unknown in it, which is the acceleration. The masses are known, and of course g is a constant. So we can solve this for the acceleration. First we'll propagate the minus sign through the quantity on the right, and then we'll move everything with the a in it to the left side of the equal sign. So we'll have big MA plus little ma equals big mg minus little mg. And if we factor out the a and the g on either side, we can arrange for a equals big M minus little m over big M plus little m times g. So this is the first answer. This is the acceleration of both masses. So now that we have the acceleration, time to start on the second part of the problem, which is to solve for the time. We're asked, how long does it take for the mass big M to fall and hit the table? We're going to assume it is released from rest. To do this, first we need to recall one-dimensional kinematics. Hopefully you recognize this equation. X minus x naught equals 1/2 at squared plus v naught t. So this is an object moving a distance x minus x naught at a constant acceleration a over a time t if it was released at a speed v naught. In our case, we have the distance that the object is moving, as the mass big M will fall at a height big H, so this is what we will call x minus x naught. So if we put that in, we simply have h equals 1/2 at squared plus v naught t. But I already said that v naught is 0. We're releasing this from rest, so that whole second term will drop off, and we have h equals 1/2 at squared. From here, we can just do the algebra to solve for t. T is the square root of 2h over a. And we know the acceleration from the previous part of the problem. The difference between the masses over the sum of the masses times the gravitational acceleration g. So if we put that in, we have the answer. This is an expression for t, the square root of 2h over the difference between the masses over the sum of the masses times g. This is the whole answer. You could just write this down for t, and that is correct, but it looks better if you don't have two fractions inside of each other like this, so we can simplify this a little bit by moving the bottom of the bottom fraction to the numerator inside the radical, and get t equals the square root of 2h times the sum of the masses over the difference in the masses times g. And this is the answer to the second part of our problem. So on to the last part of the problem. We want to know how fast the mass big M is moving when it does hit the table after the time t that we just solved for. So again, I'll remind you from one-dimensional kinematics this equation for the velocity of an object moving at a constant acceleration a for a time t if it was released at a speed v naught. And again, we're releasing this from rest, so we have v naught equals 0, so simply v equals at. So v is the speed with which the mass big M will hit the table. We've already solved for the acceleration at which it's moving, and the time it takes to hit the table, so we simply have to multiply these together. And again, this is an entirely fine solution. You could put the numbers in here and get the answer out, but again, it looks nicer if we simplify it a little bit. So what we're going to need to do is bring in the thing multiplied by the radical, squaring everything as that happens. And so of course you'll get a g squared in the numerator on the inside, and that cancels with the g on the denominator. You'll get the m minus m squared, which will cancel with one of the m minus m term in the bottom, and the m plus m will do the same thing. And so after the simplifications, we have that the speed that the block hits the table at is the square root of 2h times the difference in the masses times g over the sum of the masses. And that is our final answer for this problem. Thanks.